Hello friends, continuing with semiconductors. Today we come to its third part, doping. Now what is doping? Doping is the process by virtue of which foreign elements, trivalent or pentavalent, is added to intrinsic semiconductor as impurity in a controlled quantity 1 in 10 raised to power 23 parts to form a uniform crystal lattice. To make it extrinsic semiconductor is known as doping. I repeat, the process by virtue of which foreign elements, trivalent or pentavalent, is added to intrinsic semiconductor as impurity in a controlled quantity 1 in 10 raised to power 23 parts to form a uniform crystal lattice. To make it extrinsic semiconductor is known as doping. Now let us illustrate doping by diagram. Look at this diagram. Here silicon is doped with arsenic. And in this diagram, germanium is doped with indium. Now silicon and germanium are having 4 electrons in their outermost orbit, but arsenic have 5 electrons in its outermost orbit, and indium has 3 electrons in its outermost orbit. Now consider silicon doped with arsenic first. Now 4 electrons of arsenic are shared by 4 silicon atoms, and arsenic becomes stable. Now this electron, 5th electron, becomes free and goes to the lattice. Now consider germanium doped with indium. Now indium has 3 electrons in its outermost orbit. Indium shares its 3 electrons with 3 germanium atoms, and the 1 electron of 4th germanium atom is attracted towards indium and leaving behind a hole. So a hole is created in the crystal lattice. Thus silicon becomes doped with arsenic and germanium becomes doped with indium. Now silicon has 1 electron surplus and germanium has 1 hole surplus. Now, since free electrons are available in silicon, so it is called as negative type, because electron has a negative charge of 1.6 into 10 raised to power minus 19 coulomb. Now germanium doped with trivalent indium has a hole created in its lattice, so it becomes positive type or P type, because hole has positive charge of. This is how doping takes place. Let us recall type of bonding in semiconductors. Atoms enter covalent bonding by mutual sharing of electrons. Now type of extrinsic semiconductors. There are 2 types of extrinsic semiconductor. First is P type, second is N type. Let us take up one by one. First we take up P type material formation. When a trivalent impurity like indium, aluminium or boron is added to intrinsic semiconductor in a controlled quantity 1 in 10 raised to power 23 parts to form a uniform crystal lattice, the semiconductor becomes P type or positive type. I repeat, when a trivalent impurity like indium, aluminium or boron is added to intrinsic semiconductor in a controlled quantity 1 in 10 raised to power 23 parts to form a uniform crystal lattice, the semiconductor becomes p-type or positive type. P for positive. Now how it takes place. Let us look at this diagram. Indium shares 3 electrons with 3 germanium atoms because it has 3 electrons in its outermost orbit. What about the fourth? The fourth electron is shifted from germanium towards indium, leaving behind a hole in it. That is, electron of germanium atom moved to indium because of more chemical affinity. That is, electron of germanium atom moved to indium because of more chemical affinity, leaving behind a hole in the lattice and making indium a negative ion. Indium develops a negative charge on it and becomes a negative ion because it accepts an electron from germanium, and germanium has a hole created in the lattice. The electron which shifts from germanium to indium leaves behind a hole in the crystal lattice and becomes a p-type, positive type material because hole has a positive charge. Now let us look at the salient features of p-type material. Now first, representation by diagram. How we represent a p-type material in diagram is as shown. Positive represents holes and negative in circle represents ion, and negative without circle represents electrons. This is how we represent a p-type material by diagram. Positive are holes, negatives are electrons, and negative in circle are ions. Okay. Second, holes are in majority in p-type material. NH is more than Ne. That is, number density of holes is more than number density of electron and are called as majority carriers, denoted by positive sign. 3. Electrons are in minority. That is, number density of electron is less than number density of holes and are called as minority carriers and are denoted by negative sign. Fourth, it contains negative ions denoted by negative with the circle. Fifth, conductivity, sigma x, x for extrinsic, equal to Ne into E into mu E plus Ne into E into mu H, or it is equal to, we take out E common, within bracket we write Ne mu E plus NH mu H. Sixth, energy band diagram is as shown. Acceptor level lies near valence band. Energy gap between acceptor level and valence band is very small, of the order of 0.05 to 1 electron volt. Okay. Now second, N-type material formation, that is negative type material formation. How it takes place, let us see. When a pentavalent impurity like arsenic, antimony, bismuth, phosphorus or boron is added to intrinsic semiconductor in a controlled quantity 1 in 10 raised to power 23 parts to form uniform crystal lattice, the semiconductor becomes N-type or negative type. N for negative. I repeat, when a pentavalent impurity like arsenic, antimony, bismuth, phosphorus or boron is added to intrinsic semiconductor in a controlled quantity 1 in 10 raised to the power 23 parts to form a uniform crystal lattice, the semiconductor becomes N-type or negative type. Now look at this diagram where silicon has been doped with arsenic. Now 4 electrons of arsenic are shared by 4 silicon atoms. An unpaired electron of arsenic becomes free in the lattice and making arsenic as positive ion. So this is the unpaired electron which becomes free in the lattice. Since arsenic loses 1 electron, so it becomes positive ion. Okay. This is how negative type N-type material is formed. Now salient features of N-type material, that is negative type material. Number 1, representation by diagram. N-type materials are represented by diagram as shown here. Negatives are electrons and positives are holes, and positive in circles are positive ions. Second, electrons are in majority, that is number density of electron is more than number density of holes, and are called as majority carriers, denoted by negative signs, minus. 3. Holes are in minority, that is number density of hole is less than number density of electrons, called as minority carriers, denoted by positive signs, these positive signs. 4th, contains positive ions, denoted by positive in circle. 5th, conductivity sigma x is equal to Ne into E into mu E plus NH into E into mu H is equal to E common Ne into mu E plus NH into mu H. 6th, energy band diagram is as shown. Here donor level lies near conduction band. This is donor level which lies near conduction band. Energy gap between donor level and conduction band is very small, of the order of 0.05 to 0.1 electron volt. So this is energy gap. Donor level lies near conduction band, and energy gap between conduction band and donor level is 0.05 electron volt to 0.1 electron volt. Okay. Assignment 14 continued. Question number 13. Pure silicon at 300 Kelvin has equal electron hole concentration of 1.5 into 10 raised to the power 16 per meter cube. Doping by indium increases hole concentration to 4.5 into 10 raised to the power 23 per meter cube. Calculate Ne in the doped silicon. So here is the answer for it. Question number 14. How is a sample of N-type semiconductor electrically neutral though it has an excess of negative charge carriers? Question number 15. Carbon and silicon are known to have similar lattice structures. However, the 4 bonding electrons of carbon are present in second orbit while those of silicon are present in third orbit. How does this difference results in difference in their electrical conductivities? You answer these questions on the basis of the text that you have learnt. Thank you so much. Next time we'll take up next part of it, that is fourth part of it, p-n junction. Till then, goodbye and good luck to you.